Hi everyone, my name is Marcin, and if you're doing some really last minute review, this video might help you with short question number 2 on the final exam from year 2006. So last night, during Phil's review session, a few students brought to attention the concern that the answer provided for this short question is actually incorrect, and the following discussion was a bit brief and vague, so I thought I'd give a more complete and full reasoning of why the solution provided on the website is not necessarily correct. So, as you'll recall, short question number 2 just consists of a third order differential equation with associated initial conditions, and we're asked to state whether or not a solution to this equation exists without actually trying to solve it. The provided answer is that since this is a third order differential equation, it requires 3 initial conditions, and since 4 are provided, so 1 too many, there's not going to be a solution. So there's actually a problem with this answer, and it can be illustrated very well with a counterexample. So consider the following example. We have the following second order differential equation, fairly simple, and we have these 3 associated initial conditions. So immediately, if we go on the reasoning given in the answer above, since this is a second order differential equation, we only need 2 initial conditions, and the third one is 1 too many, so we will not have a solution. But let's see what happens when we go ahead and try to solve this guy. Our characteristic equation, of course, is r squared plus 1. Solving gives r equals plus minus I, and then we arrive at our general solution. Y is a times cosine x plus b times sine x. So now let's apply the initial conditions. Applying the first one, we evaluate our general solution at 0, and we know that this must be equal to 0. And this gives us the value of a, which has to be 0. So we update our solution. We now have that y is just b sine x, and we go ahead and apply the second initial condition, that we take the derivative of y and evaluate at 0, and we know that this has to be 1, and this gives us that b, the constant b, must be 1. So now we can update our solution again. We have just y equals sine x, and all our constants are gone, so we've actually arrived at a solution, but we still have one more initial condition to go, so let's apply it and see what happens. We take the second derivative of our solution and evaluate it at 0, and we know that this must be equal to 0, and in fact it is. So we have found a solution to the system, sorry, not the system, but the equation rather, and the initial conditions, and it's just y equals sine x. So how come we're able to find a solution here? Well, the issue is that as long as the initial conditions given are consistent, meaning that they kind of that there's some initial conditions that are redundant, that give the same information as previous combinations of initial conditions. So as long as all the initial conditions kind of agree with each other, you can have an arbitrary number of them and still end up with a solution. So as an analogy, you can think of a system of linear equations with m equations and n unknowns. You can actually have as many equations as you like, provided that there are no more than n non-redundant equations, you can still have a solution to this system. So how do we actually approach short question number 2? Well, a good way to solve it is just the question here. So we remind ourselves of what it was. For these 2 initial conditions here, I just plugged in the fact that y of 0 is 1, so we have a slightly more simple representation of these 2 initial conditions. So how do we solve this short question number 2? We just take our differential equation and we set x equal to 0, and then we can apply our initial conditions. So the first term is just 0 from this initial condition. The second term is something, but it essentially goes to 0 because it's being multiplied by x, and that's being set to 0. This third term, dy dx, is negative 2, as we see from this equation. And the final term, y, is just 1, as we see from this initial condition. And all of this has to equal 0. And if we simplify the left-hand side, we see that we have to have negative 1 being equal to 0, which is never going to happen. So we can conclude that there is in fact no solution to this differential equation without even having to solve it. Okay, thank you very much, and good luck on the final.